Good day. We are the fifth group. Today, we are going to discuss our virtual laboratory on batch flow reactor.
Reaction kinetics studies in a batch reactor. For the introduction, we have Diana. Batch reactors are used for most of the reactions carried out in a small-scale operation, hence it is the preferred reactor in the laboratories and pharmaceutical industries where small volumes of high-value product are made. According to Fogler HS 2016, batch reactors are beneficial for testing new processes that have not been fully developed, as well as for the manufacture of expensive products, and for processes that are difficult to convert to continuous operations. When it comes to its working principle, batch reactor describes no continuous flow of reactants entering the system or products leaving the system while the reaction takes place. It is also a closed system which total mass of each batch is fixed. Moving on to the experimental setup, we have Carol Jade. For the virtual setup, the volume of the reactor was set to 1 liter, and the stock concentrations of both ethyl acetate and sodium hydroxide was set to 0.040 m. Based on the initial molar ratio of the reactants, the volume of the sodium hydroxide and ethyl acetate was calculated. The conductivity was noted for varying temperature of each initial molar ratio of the reactants. This is the virtual laboratory setup, wherein the conductivity meter probe has one end that is connected to a measurement device, such as a computer. We then input the calculated volumes of the solutions. The obtained volume of the sodium hydroxide was added into the reactor and mixed with a stirrer. The heater was also switched on to reach the desired temperature. When the required temperature in the reactor was maintained, we then added the ethyl acetate solution and started the stopwatch. The conductivity was noted down at different time with intervals of 30 seconds. This procedure was continued until no change in the value of conductivity meter reading was observed. The experiment was repeated at various temperatures, and lastly observations and tables for the raw data were recorded and filled out respectively, and proceeded to calculations. To discuss the results of the experiment, we have Sherry May. As we conducted the experiment, we set the molarity from 1.2, 1.4, 1.6, 1.8 and 2 while the temperature ranges from 30, 33, 36, 42 and 45 degrees Celsius. We also set the time via 15 seconds interval from 30 to 345 seconds. It has been observed in the compiled data that the higher molarity along with higher temperature means higher conductivity and higher rate constant. Based on the computed data, the 1.2 m has CaO of 0.0182 and CpO of 0.0218, 1.4 m has a CaO of 0.0168 and CpO of 0.02332. 1.6 m has a CaO of 0.0154 and CpO of 0.0246. 1.8 m has CaO of 0.01428 and CpO of 0.02572. And lastly 2m has a CaO of 0.01332 and CpO of 0.02668. Also, it is indicated at the calculated data from 1.2 m that the rate constant for the saponification of ethyl acetate with NaOH at a temperature of 30 degrees Celsius is 8.76. Using the calculated value of activation energy for the reaction, 106,852 J per mole, and frequency factor Ko, 7.60 times 10 raised to 18. At 1.4 m, the rate constant for the saponification of ethyl acetate with NaOH, at a temperature of 30 degrees Celsius, is 8.78. Using the calculated value of activation energy for the reaction, 36,451 J per mole and frequency factor Ko, 1.78 times 10 raised to 7. At 1.6 m, the rate constant for the saponification of ethyl acetate with NaOH, at a temperature of 30 degrees Celsius, is 8.03. Using the calculated value of activation energy for the reaction, 27,114 J per mole, and frequency factor Ko, 4.35 times 10 raised to 5. At 1.8 m, the rate constant for the saponification of ethyl acetate with NaOH at a temperature of 30 degrees Celsius, is 7.97. Using the calculated value of activation energy for the reaction, 27,813 J per mole, and frequency factor Ko, 5.78 times 10 raised to 5. And lastly, at 2m, the rate constant for the saponification of ethyl acetate with NaOH at a temperature of 30 degrees Celsius, is 9.31. Using the calculated value of activation energy for the reaction, 94,588 J per mole, and frequency factor Ko, 7.62 times 10 raised to 16. The rate constants from the calculated data at 30 degrees Celsius is increasing when it comes to 1.2 m, 1.4 m and 2 m, but gradually drop in 1.6 m to 1.8 m. For the calculations, let's go back to Diana. Tabulated formulas were provided. Total volume times open parenthesis 1 plus molar ratio times stock concentration of ethyl acetate divided by stock concentration of sodium hydroxide close parenthesis raised to -1 is equal to the volume of ethyl acetate. While volume of sodium hydroxide can be obtained by subtracting the obtained volume of ethyl acetate to the total volume, which is 1000 milliliters. Moreover, for obtaining the initial concentrations of ethyl acetate and sodium hydroxide, the formula is stock concentration of the species times volume of the species divided by total volume. Next is the temperature compensation for conductivity meter, which is Y sub 28 is equal to conductivity reading from raw data times open parenthesis 1 plus 0.0145 times the set temperature minus 28 close parenthesis. Next is the formula for concentration of ethyl acetate, which is equal to initial concentration minus open parenthesis initial concentration of sodium hydroxide minus concentration of sodium hydroxide close parenthesis. Then for obtaining the concentration of sodium hydroxide, the formula is 0.00026 multiplied by the obtained Y sub 28 minus 0.000063. And lastly, for obtaining the conversion, formula is X sub A is equal to 1 minus concentration of ethyl acetate divided by initial concentration of ethyl acetate. The following data were the obtained calculations for different molar ratios. To state the conclusion, let's hear it from Andrea. Based on the experiment performed in the graphs shown, we can therefore conclude that with higher temperature and molarity, higher values of conductivity and rate constant can also be attained. The order of reaction, which is assumed to be n equals 2, and the reaction constant K, can be obtained both graphical and analytical. While values of rate constant and activation energy of varying molarity and temperature can be observed at the abstract part, errors might be possible for the reason that the data presented is too large. Thus, may affect the results. For the last part, here are the actual experiment hazards. For the hazardous effects of ethyl acetate, firstly, on the eye, its vapors can cause eye irritation. When this is inhaled, it may cause irritation of the digestive tract. It can also cause headache, nausea, fatigue and dizziness. Inhalation of high concentrations may cause narcotic effects. If it touches the skin, it may cause skin irritation. Prolonged exposure may cause drying and cracking of the skin. Lastly, when ingested, can cause respiratory tract irritation. For the hazardous effect of sodium hydroxide, for the eyes, may cause eye burns, blindness and corneal damage. When inhaled, it may cause severe and permanent damage to digestive tract, gastrointestinal tract burns and perforation of the digestive tract. May also cause severe pain, nausea, vomiting, diarrhea and shock. Contact to skin can cause skin burns and deep penetrating ulcers of the skin. If ingested, it may lead to chemical pneumonitis and pulmonary edema. It can also cause severe irritation and chemical burns to the respiratory tract with coughing, burns, breathing difficulty and possible coma. Thank you for listening.